Let's now move towards answering the questions that we posed previously. So the first question is there a systematic way of finding the eigenvalues? The answer is yes, actually. So we saw one way of finding the eigenvalues and eigenvectors for a given matrix, and it was that, simplify this AX, in other words, solve this system AX equal to lambda x for lambda first, actually. And once you find the lambda, then solve it for x. Okay, that's going to give you the eigenvector. So this is one of the things. And if you go back now to one of the lectures, for example, in the last lecture, maybe I think the second or third part, in which I talked about the different characterizations of the eigenvalues. Okay, so there was some characterizations of eigenvalues. So we know that lambda is going to be an eigenvalue of the matrix A if this is satisfied, and I can also write this as this, actually, lambda x minus ax equal to 0, and I can say that this is going to be lambda I minus a operated onto x equal to 0. So the second condition was that this system has a non-trivial solution. Okay, non-trivial solution. In other words, lambda is going to be the eigenvalue of the matrix A if this system has a non-trivial solution. And a third condition that we did, which is equivalent to this condition, was that this matrix lambda I minus A is not invertible, actually. Okay, it's not invertible. So if it is not invertible, that means it must be singular, and hence its determinant must be, okay, its determinant must be 0. Its determinant must be 0. So from this observation, it turns out that if the lambda is eigenvalue of the matrix A, then lambda is a solution to this polynomial, actually. So if you consider, for example, a polynomial Pa of x, and you define it by the determinant of, say, xi minus a, then lambda is the eigenvalue of the matrix A if you substitute lambda into it and it turns out, okay, in other words, if you compute Pa of lambda and it turns out to be 0. Because if Pa of lambda would be 0, that would mean that the determinant of lambda I minus A is 0. And if the determinant of lambda I minus A is 0, that means lambda I minus A is not invertible. And if it is not invertible, this has a non-trivial solution, or this is satisfied, actually. In other words, you're going to find some lambda, interesting lambda and x, actually. So in other words, for finding the eigenvalues of a matrix A, it is interesting to look at the roots of this polynomial, actually. Okay? It is interesting to look at the roots of this polynomial. We're going to later call this polynomial as the characteristic polynomial, actually. Okay? Because if you have characteristic polynomial, find its root, and its roots are the eigenvalues. Okay? Now let's see the characteristic polynomial. Let's study the characteristic polynomial in case of the different kind of matrices, actually. So M is a square matrix. So if I take n equal to 1, in other words, I assume that A is a 1 by 1 matrix. Okay, it's a 1 by 1 matrix. What would be this polynomial corresponding to this matrix A? So it's going to be determinant of xi. What would be the I in 1 by 1 case? It's going to be simply 1. So it's going to be x minus A is A11. So what would be the determinant of x minus A11? Okay, so it's going to be equal to x minus A11. It's just a 1 by 1 matrix, actually. Okay, so if you have a 1 by 1 matrix, PA of X has this form. How about if A is n is 2? In other words, A is a matrix of this form: A11, A12, A21, and A22. Okay, so what would be this polynomial for this matrix A actually? So this is going to be the determinant of the matrix xi minus A. So I is 1, 0, 0, 1. So x multiplied means x 0, 0, 1. So it's going to be a matrix x minus A11 minus A12 minus A21 and x minus A22. Okay, this is going to be the polynomial. So if you calculated PA of x, okay, if you calculate the PA of x, this would be what? This multiplied by this actually. So it's going to be x minus A11 multiplied by x minus A12, A22 minus A12, and A21 actually. Now if you simplify this a little bit more, so this is going to be x squared minus, if you simplify it, A11x, A22x is going to be A11 plus A22x and plus A11, A22 and minus A12 and A21. This is what it is going to be. Now when you look at these two numbers, do you find any interesting relationship between these two numbers and the matrix A? The answer is there is an interesting relation. This A1 plus A2 is really the trace of the matrix, so it's going to be the trace of the matrix A multiplied by X plus, okay, A11, A22, so A11 multiplied by A22 minus this difference, this is really the determinant of the matrix A actually. So for a given 2 by 2 matrix, okay, for any given 2 by 2 matrix, this polynomial, mysterious polynomial, we're going to call it letter characteristic polynomial, whose roots are the eigenvalues of the matrix A, is going to be this actually: x squared minus trace of Ax plus the determinant of A actually. This is going to be really the polynomial. I want to write this explicitly in case of n equal to 3 as well, and then I want to generalize this, that okay, if you have n by n matrix, how does and what does this polynomial would look like explicitly. So it's going to have a suite form. Now if I take, for example, n equal to 3, then my matrix is going to be Aij, okay, where you know I and j are 3 by 3, A11, A12, A13, so on and so forth. Okay. What would be the polynomial PA of x? So it's going to be the determinant of x minus AI. So it's going to be the matrix x minus A11, x minus A22, x minus A33 actually. And rest of the entries just negate them. Minus A12, minus A13, negative A21, negative A23, negative A31 and negative A32 actually. A32. So this is what is going to be the determinant of it. So we can compute this determinant. Okay. We can compute this determinant. So I'm directly writing its determinant actually in the form of a polynomial. So it's going to be z cube plus, let's call c2z, or maybe x cube plus c2x plus c1, c2x square plus C1x plus C0, okay, where the C2, C1, C0 are the numbers in the terms of A's, and let me explicitly mention it. The C0 is the minus determinant of A. By the way, when it was 2 by 2 matrix, it was plus determinant of A, and now the last term here is minus determinant of A. So if n is 3, the C1, okay, C1 is C1 is a big number, so it goes like A11, A22 minus A12, A21 plus A11, A33 minus A13, A31 plus A22, A33 minus A23 and A32. This is what the C1 is, and the C2 is really minus A11 plus A22 plus A33, which can be again treated as the trace of the matrix A. In other words, it's the minus trace of the matrix A actually. Okay? Minus trace of the matrix A. So what does this actually shows? What does this actually shows? I'm gonna write a theorem. I'm not gonna prove it actually. That is going to say that if you have an n by n matrix, the first term is going to be x power n. The next term, Cn minus 1, is going to be the trace of the matrix always, and the last term is going to be the determinant of the matrix A actually, okay, with a plus minus sign, while all other constants are going to be the numbers in the terms of the entries of A. Moreover, the coefficient of the higher power, it is always going to be 1. So it's going to be a monic polynomial actually. Okay, so it's a polynomial in which the degree, the highest degree term has the unit polynomial, unit coefficient actually, the one coefficient. Okay, so let me write a theorem. I'm not going to prove it. Okay, I mean if you are interested, you can see it. The proof is interesting. But it's going to unnecessarily take some time, so I'm going to focus on the more important things actually. So here is the theorem. So it says that if you have a matrix n by n, and the polynomial p of x means determinant of xi minus a, then this polynomial P of x is going to be an nth degree polynomial that has this form. In other words, its first term is always going to be x power n minus cn minus 1 x power n minus 1 plus cn minus 2 x power n minus 2. So it's going to be a polynomial with the alternating terms. Okay, it's going to be polynomial with the alternating terms, and or maybe if you wish, you can put a plus and then write the alternatingness in the in the coefficient actually. Okay, by putting minus 1 power n. So Pa is x power n cn minus 1 x power n minus 1, so on and so forth, plus c1x plus c0 c0 actually. Okay, this is what it is going to be. Where C0 is always equal to minus 1 power n times the determinant of A. Okay? So in other words, if n is 1, it's going to be minus determinant of A, as we saw previously. If n is 2, it's going to be plus determinant of A. If n is 3, it is again going to be the minus determinant of A, and so on and so forth. Okay, C naught is minus 1 power n times determinant of A. Cn minus 1. This is always going to be the trace of A actually. Okay, this is always going to be trace of A. So it's going to be minus 1 power n again times, or it's going to be, sorry, always minus trace of A. It's going to be always minus trace of A. Moreover, lambda is going to be an eigenvalue of A if and only if it is the root of this polynomial actually. Okay? It is the root of this polynomial. So first of all, if a given matrix A, so its determinant of x minus ai, in other words, this polynomial Pa of x can be explicitly written in this manner, in which C naught is always going to be this and Cn minus 1 is always going to be this, and any value that is an eigenvalue of the matrix A, okay, it is the root of the eigenvalue or root of this polynomial actually. And we saw it previously. I mean, the thing that I mentioned just before was that, you know, if you want to study the eigenvalues of the matrix, then you have to study this polynomial, determinant of x minus ia. Okay, you have to study this polynomial, because we saw from there that if the lambda is eigenvalue, then determinant of x minus I at lambda, in other words, determinant of lambda I minus a, that is going to be equal to 0. In other words, one side of it we already know actually. The other side is also not difficult to prove. Okay, so this is an interesting result actually that tells us that if you want to find the matrices, the eigenvalues of A, go and study this polynomial, okay, which is of this form, because all roots of this polynomial are eigenvalues, and any value that is eigenvalue is going to be the root of this polynomial actually. Okay, is going to be the root of this polynomial. We call this polynomial characteristic polynomial definition. So I can put the definition now that, you know, this polynomial Pa of x, that is determinant of xi minus a, is called the characteristics polynomial of A. Okay. Now, what would be the systematic way to find the eigenvalues and eigenvectors of the function? The step one, always, whenever for a given matrix you want to find the eigenvalues and eigenvectors for a given matrix, you have to take these steps. Step one, compute Pa of x for the given matrix. Okay. Step two, solve this Pa of x equal to 0. Okay. And as a solution, if you get, say, for example, some lambdas, lambda 1, lambda 2, I don't know, lambda d, you get some eigenvalues. So these are going to be the roots of the equation. So when you're going to solve, you're going to get these numbers, and these numbers are going to be the eigenvalues of the matrix A. The step 3 is going to be to find the eigenvectors corresponding to each eigenvalue. In other words, what will be the eigenspace of each of these eigenvalues? And in order to find the eigenspace, in other words, the eigenvectors corresponding to each one of these vectors, solve to find, okay, to find eigenvectors, solve this Ax equal to lambda I x for all these values. So this is going to give you the eigenvectors corresponding to the eigenvalue lambda I, which is also going to be the eigenspace of the matrix of the eigenvalue lambda I. So if you can solve, so if you can find all such x, collection of all such x which satisfy this is going to be the eigenspace of the eigenvalue lambda actually. Okay? So that's what essentially you have to do. The more systematic way. You don't have to go here and there to find the eigenvalues. I mean, you can compute. You can take, for example, the same matrix. Take this matrix A equal to 1, 1, 0, 1. Okay, so what would be the PA of x? So it's going to be the determinant of the matrix x minus 1, minus 1, 0, and minus 1, x minus 1. Okay? And this is going to be x minus 1 square actually. So if you equate it to 0, obviously you're going to get x equal to 1. So this is the eigenvalues. Okay? So corresponding to this, this is the only eigenvalue, okay, that you get actually, because the characteristic polynomial has only one root, which is, you know, x equal to 1 or lambda equal to 1. And then we also computed previously its eigenspace and eigenvectors. I'm not going to repeat it actually. How about if you have an upper triangular matrix? So imagine you have a matrix of this form. Imagine you have an upper triangular matrix. Okay, let's just talk about, say, ABC 0 DE 0 0 F actually. So you can even take, for example, general n by n matrix, upper triangular matrix. What would be the polynomial? What would be the eigenvalues of the polynomial, the upper triangular matrix? So what would be the PA of x? So it's going to be the determinant of A minus x minus A minus B minus C 0, x minus D minus E 0 0, and x minus F. What would be the determinant when you're going to compute? We know about the upper triangular matrix or the lower triangular matrix. The determinant is simply the product of diagonal entries. So it's going to be x minus A, x minus D, x minus F actually. Hence, A, D, okay. So this is really the characteristic polynomial of an upper triangular matrix. So what would be the eigenvalues of it? So it's going to be A, D, and F, because if you equate them to 0, so x is going to be A, D, and F are the eigenvalues of this matrix actually. In other words, the diagonal entries are eigenvalues of this matrix. So if you have any upper triangular matrix or lower triangular matrix, you don't have to even solve, for example, the characteristic polynomial. Its diagonal entries are really the eigenvalues of the matrix actually. Okay, this is an interesting conclusion. So let's now move towards another interesting topic, which is, so we saw previously what do we mean by the geometric multiplicity. The geometric multiplicity was the dimension of the eigenspace actually. Now we would like to define the algebraic multiplicity. Okay, the algebraic multiplicity. So let's start with, for example. So let's take the same matrix A1 0 0 0 0 1. So when we computed the characteristic polynomial of it, it turns out that you're going to have x minus 1 square. In other words, 1 is the eigenvalue, but this factor x minus 1 is appearing 2 times actually. So I'm going to say the algebraic multiplicity of an eigenvalue is the number of times this factor appears in the characteristic polynomial actually. So since x minus 1, in other words, the factor containing the eigenvalue lambda appears 2 times in the polynomial, so you're going to say the algebraic multiplicity of the eigenvalue 1 is 2 actually. Okay? So let me define it kind of a more general manner. Imagine you have a polynomial that goes like this for a given matrix, which is like x minus lambda 1, x minus lambda 2, so on and so forth, and x minus lambda n actually. X minus lambda n. Now in this polynomial, these lambda 1, lambda 2, lambda n, they all, it is not necessary that all of these numbers should be different actually. They all can be same actually. In other words, lambda 1 can appear 2 times or 3 times or some number of times. Okay? So it can appear some number of times. For example, the characteristic polynomial for this matrix is x minus 1 times x minus 1. So here lambda 1 is 1 and lambda 2 is also 1. So in other words, one eigenvalue repeats 2 times. So if I have a matrix A, its characteristic polynomial is going to be n degree polynomial, in which there can be repeated eigenvalues actually. In other words, you can have the same number appears more than 1 times in this factorization actually. So if I write this as this, that this is equal to x minus mu1 power say n1, x minus mu2 say power n2, so on and so forth, and x minus mu d power nd. In other words, and what is mu1? Mu1 can be any number, lambda 1, lambda 2, lambda n. Mu2, this can be also any number, lambda 1, lambda 2, lambda n, but it's going to be different from mu1. It's going to be different from mu1. And lambda, mu d can be any number, lambda 1, lambda 2, lambda n, but it's going to be different from all previous number n actually. Okay? Where okay? In other words, when you consider the spectrum of the matrix A, it is these numbers, mu1, mu2, mu d. Okay? But the factor consisting of the mu1 can appear n1 times. Obviously, the sum of these n1 plus n2 plus nd, this should be equal to n. Okay? In other words, I can have a polynomial which has this form x minus 1, x minus 1, x minus 2, x minus 2, x minus 2. So okay, you can have this polynomial actually. So it has the 5 factors, but one of the factor is repeating actually. So in other words, this can be written as x1 minus what do you call x minus 1 square and x minus 2 cube actually. Okay, I can write this as x minus 2. What would be the spectrum of a matrix with this polynomial? Is going to be 1 and 2. It's not going to be 1, 1, 1, 2, 2, 2. Okay, because you just have to write them once actually. Okay, so and sum of these powers has to be equal to what you call the total number of brackets that you have. In other words, whatever is the order of the matrix. So in other words, some factors in the characteristic polynomial can repeat. So if x minus 1 is repeating 2 times,